Hello student, welcome to the Web Optics course. Today we have lecture number 40 and in today's lecture we will going to discuss about the grating, the resolving power of the grating. So we have lecture number 40. I am going to discuss resolving power. Okay, so let me remind what we have done in the last class, that if we have a grating spectra for two different wavelength, then let me draw it. So this is the spectra for grating spectra and so on. This is a grating spectra for one particular wavelength, and if I have another wavelength, then there will be slight shift and I am going to get something like this. So these spectra, two spectra are for two different wavelength. If this is for one wavelength and this is for another, this is for another wavelength. This color is for one wavelength, say for lambda 1, and other is for another wavelength, lambda 2. So the angular dispersive power is defined by d theta d lambda, and that which is d theta d lambda, and we find that this quantity d theta d lambda, this quantity essentially is P divided by A and then cos theta. So for a given P and theta, the resolving power or the dispersive power, is proportional to 1 by A. So if the number of ruling is very high, then what happened, we will have a grating having more dispersive power. It can disperse the two wavelength, the separation between two wavelength, the principal maxima, with a larger amount compared to the grating which is having less number of line per unit length. So that means if two wavelengths are there, and if I do the experiment for two different grating, in one case the number of ruling is 100 per centimeter and in other case 1000 per centimeter. In case of 1000 per centimeter, for the same order, what we will see, the separation, the spatial angular separation between a given order will be much more in case of the grating having more number of ruling. So after that, what we try to understand, the next property or next quantity, that is called the resolving power of the grating. Resolving power of a grating. So, what is resolving power? Resolving power is the ability to distinguish two close spectral lines to close spectral line. Which is d lambda by lambda by definition. So, what is d lambda here? D lambda is the smallest wavelength wavelength difference for which spectral lines of the wavelength spectral line of wavelength is just resolved. This is the smallest wavelength which one can just resolved, and then that is the quantity resolving power. What is the meaning of that just resolved? So, let me quickly draw that spectra once again that we have done earlier. So, for one wavelength the spectral line will be something like this, and for other wavelength it is like this. So, two wavelengths are here associated. Say this is lambda plus this d lambda, and other wavelength is lambda. So, lambda and lambda plus d lambda, if we put these two together and then allow to diffract to a grating, in the spectra we will see these two principal maxima placed side by side. But what is the condition for this delta lambda? That is the minimum separation that one can, if they two are far apart, then the resolving of these two is very simple. But if it is not that, if it is close together, close enough, then it is difficult to resolve. So, what is the condition for that? Let us try to understand. So, in terms of theta, if I want to do this plot, so let me plot it then. So, this is for red, say. We have a peak here, and I am not plotting here the secondary maximus, and for other wavelength, the condition is something like this, that the minima of this wavelength should be the maxima of other. So, it should be like this. Okay, so these are the two wavelengths that we want to resolve, and how the theta is measured. So, this is the coordinate we have, and this is the way the distribution one can have, and I measure from this point, say, and this is my theta. This is a peak of and this is my theta, and this angle is d theta. So, this is my theta, and this small is d theta. So, this is the peak of, say, this is the peak of mth maxima for wavelength lambda, and this is minima for lambda. Okay. But that is also the peak of mth maxima. So, these things is also peak of the mth maxima for the wavelength lambda plus delta lambda. Okay, so that is the condition. So, if I use now the condition for maxima, then we have A sin theta is equal to m lambda and d theta is equal to m d theta divided by A cos theta that we have. Now note that when we have this function, because this is the function we are plotting, sin n alpha divided by sin alpha. So, this function has its minima when alpha is equal to S divided by N multiplied by pi, that we derived in earlier class, where S is an integer except these values 0, then n, then 2n, integer multiple of n is prohibited, this value should not be there. So, when S is equal to 1, then alpha I can write is as pi by n. N is a number of, mind it, this is a number of slits. So, similarly, if I put the condition for the maxima of lambda plus delta lambda, then maxima for lambda plus delta lambda, this condition we can also put, and it is A sin theta is changed now, theta plus d theta. So, theta plus d theta, that is equal to that is equal to 1 by n lambda plus m lambda, because m lambda is the condition for the maxima, and other order the minima condition is 1 by n. So, the next order is 1 by n s. So, I am going to get this. This is the maxima, this is the condition for the maxima also for lambda plus d lambda. So, once we have this we can write as m plus 1 by n lambda, that we have, and we already have another expression in our hand, A sin theta, that is equal to our m lambda. So, from these two we can have sin theta plus d theta divided by sin theta, that is m plus 1 by n lambda whole divided by m lambda. Just divide these two expression, that we get, this is 1 and this is 2, dividing 1 by 2 I get this. This is simply 1 plus 1 by m n. Now, for the small theta, for small d theta rather, sin theta plus d theta is nearly equal to sin theta plus d theta cos theta. So, here we have sin theta plus d theta cos theta divided by sin theta is equal to 1 plus 1 by m n. So, we have d theta is equal to something like 1 by m n tan theta. So, that is one equation again, and also we have a sin theta is equal to m lambda, and from there we also calculate that d theta is equal to m d lambda divided by a of cos of theta. So, from so this is equation 2 again. I write from 1 and 2, equating these two conditions leads us to something like 1 divided by m n, then tan theta I divide as sin theta by cos theta, and that side we get m d lambda divided by a of cos theta. Cos theta we are going to cancel out, and eventually I have 1 by m n sin theta is equal to m d lambda by a, where sin theta again is m lambda divided by a from the condition. So, we are just playing with the expression to get what is the expression of. So, our goal is essentially to find out what is the expression of d lambda divided by lambda, that is the resolving power of the grating, and we need to find out what is this value under that condition, under just a resolving condition. And what is the just resolving condition? I am going to explain again. So, let me finish this calculation, we are almost done. So, sin theta is this. If I replace this, so eventually we have 1 by m n multiplied by m lambda divided by a is equal to m by a d lambda. So, this m 1 m will cancel out, a cancel out. So, we have we have d lambda by lambda. So, lambda divided by d lambda is equal to lambda divided by d lambda is equal to m multiplied by n. Okay, that we are getting. Let me check once again. Mn is lambda divided by d lambda. Yeah. So, this is the quantity we are looking for, and if I go back to our original thing. So, what is the spectral ability of distinguish of two closely spaced spectral line, and that is the quantity we are looking for. And so from this expression we can see that if this quantity d lambda by lambda is 1 by mn. So, if n is very high, the point is if n is very high, if this is the grating number or the number of ruling, this is the number of slits. So, number of slits, if it is very large, then what happened? We have this d in d lambda by lambda quantity very small. That means we can resolve even a very small wavelength by using that particular grating whose number of slit is very large. Number of slit is very large, that means the grating, the ruling per unit length is large. So, how we resolve that? What is the condition for resolving? The resolving condition, just about to resolve to spectra, is this. If I have a spectra peak, central peak this, and here we have a minima of that, and exactly at that point if I have the maxima for other wavelength, then that is the condition for just resolving. So, here that condition we exploit, and when we exploit that condition we find that, so that is the condition, for maxima of lambda, and that is the condition for minima of lambda plus d lambda, that is the condition for maxima of lambda plus d lambda, but that is also the condition for the minima of lambda. So, these two condition we combine together, and after combining these two we find that this quantity d lambda divided by lambda, that quantity is 1 divided by mn. If that means if the number of slits are very large, then we can have small wavelength separation, and that small wavelength separation can be resolved. This is the amount of the wavelength separation that we can resolve compared to a given wavelength lambda. So, that we can able to resolve. This delta lambda will reduce more if the number of slits is more. So, delta lambda will be small, I mean even a smaller wavelength can be resolved with the grating for which we have the number of slits n is very high. So, today we have that much. So, we discuss in detail about two important property of grating. One is its resolving power and another is the this diffraction, and this resolving power we find it directly related to the number of slits, and if we increase the number of slits of a given in a given grating, then that grating essentially will have a more resolving power. So, with this note I like to conclude here. Thank you very much for your attention and see you in the next class.